All right, so we'll finish up section 6.2. Okay, we're going to look at a couple different things in this section. The first thing we'll look at is tied in with unit circle trig. Okay, again, how we can find not just the sine, the cosine, tangent, secant, cosecant, cotangent of the quadrantal angles, but we're going to start to do it for angles that are not right on the axes. Okay, specifically, we're going to do it for angles that are multiples of 30, 60, and 45. And what we'll do is we'll start just by finding the trig functions of these angles. And if you can do the three that I've written here, then doing multiples of them is very straightforward. Okay, and the other thing we're going to do a little bit in this section is start to work with trig identities. Trig identities is something we're going to spend at least another 2, maybe 3 classes on. So it's not something we're going to like start and finish today. It can be a challenging topic, but we're going to just look at the very, very, very basic stuff with it. And there'll be one question on the test with trig identities. And towards the end of class, I'll show you one very similar that's going to be on the test. Okay, so that's kind of just our goal for today. All right, so I'm going to start by looking at the 45-degree angle. And my goal is to find all 6 trig functions, eventually, of 45 degrees. Okay, so that's what I want to be able to do. But in order to do that, what do I need to know about 45 degrees? Yeah, I got to know the coordinate for it. So what I'm going to do is create a shape within this circle. And this line that I just drew, or that ray, is going to be one of the sides. Does anybody know what shape specifically I'm going to create? Yeah. What kind of triangle? Yeah, I'm going to create a right triangle by drawing in the height perpendicular to the x-axis. All right, so that's a 90. The angle here is 45. You can kind of think of that as almost like an angle of elevation. What angle would you have to go up to get to 45 degrees? So now, if that's a 45 in the lower left, what about the angle at the top? 45. Right, how come that's also a 45? Yeah, they all have to add up to 180. Or the 2 acute angles have to add to 90. Whatever way you want to say it. So what I've done is I just drew a bigger copy of the 45, 45, 90 triangle down here so I can work with it a little easier. Now, is there anything I already know in that triangle besides the angles? Tiny?
Right side and the bottom side
Okay, that's very important. I know that the height and the base are the same, but I don't know what they are, so how could I represent them? Oh, like a congruent symbol? Yeah, you could do that. And now how would I represent them if I was going to make an equation? Yeah, I would just pick a letter and use the same letter for both. See, I wasn't as specific as I was looking for. Now that's good, but I need something else. There is an equation I can use that has to do with the sides of a triangle, but you need more information than we have here.
The length of the hypotenuse is 1.
Yeah, the length of the hypotenuse is 1 because that's a unit circle, and the hypotenuse is the radius of the unit circle. Right? Now I've got enough information to do what I want. Anybody think of a formula you can use involving the sides of a right triangle that helps you to find out how long a side is if you don't know it? Yeah, the Pythagorean Theorem. So can anybody set up the Pythagorean Theorem for me using what I have in this triangle? Yeah. Yeah, you've got x squared plus x squared equals 1 squared. Combine your like terms, you get 2x squared equals 1. And now I need to finish solving that for x. Okay, so what's x? Or what's my next step to get x? Yep, divide each side by 2. And my last step, how do you get rid of the square? Take the square root. And how do you square root a fraction? Take the square root of the top and the bottom separate. So the square root of the top just becomes 1. Square root of the bottom, well, we can't simplify it. We just leave it as square root 2, but we can simplify that whole fraction. Or we can at least rewrite it, maybe as a better way. Yeah? You get the square root of 2 over 2. So now I know the length of this side and the height of that side. So why does that help me? Well, if you are starting at the origin, which is that point right there, you need to go right a certain amount and up a certain amount to get to that point. The amount you go right and the amount you go up is the length of the sides. So how far to the right did I go? Square root 2 over 2. And then how far up? Square root 2 over 2. So the coordinates for 45 degrees would be what? Yeah, square root 2 over 2, comma, square root 2 over 2. And in the homework last night, that was one of the problems, to find the 6 trig functions of this coordinate, but I hadn't told you that it was the coordinate for 45 degrees. Now you hopefully can see where that coordinate comes from. Okay, and that's always the coordinate, so at this point it's good to know that and memorize that coordinate. Now, if we want to deal with 45-degree angles in other quadrants, okay, like 135. Any guess what the coordinate would be for 135? Yeah, the only thing that happens when you do the multiples of 45 is you're in different quadrants, and either the x or the y or both could become negative. What would be the degree measure of a 45-degree angle in quadrant 3? Yeah?
Negative 2 square root of 2 over 2. Wait, negative square root of 2 over 2. The same.
Okay, so that would be the coordinate, and what angle would that represent? Kyle, you gonna help her out? Well, this is 180, so it's past that. It's 225. Remember, if it's a multiple of 45, and it's in the quadrant, it's got to end in a 5. All right. And then the last one you could do is over in quadrant 4. And the coordinates there would be root 2 over 2, negative root 2 over 2. But what would be my angle? 315. Yep. So any one of those 4 angles you should be able to do pretty quickly as long as you know the coordinates for quadrant 1. You've got the numbers. You just have to take into account negatives in other quadrants. Right, so that's your 45, 45, 90. Any questions on that? All right, so the next one we're going to look at is the 30, 60, 90. Right, so what you would have is something like that. Okay, here's your circle. And I'm going to sketch, let's do the 30-degree angle. Okay, so it's going to be closer to 0 than it is to 90. Here's my triangle. That's 30 degrees. So that means this angle right here at the bottom, that's 30. And then the angle at the top has to be 60, but how come? It's all going to add up to 180. And so like I did last time, I've drawn the same triangle bigger off to the left so I can easily write some stuff down. Now, is this the same kind of triangle as the 45, 45, 90? No, it's not isosceles. All the sides are different because all the angles are different. but I at least know one of the sides. What side do I know? Okay.
Hypotenuse.
I know the hypotenuse is how much?
1.
1, and how come?
Because it's the radius of the circle, which is a unit circle.
Yeah, the hypotenuse is the radius on the unit circle. All right, now I need the other two sides. So since they're different, if I want to use the Pythagorean theorem, I'd have to call one letter and one a different letter. But what would be the problem if I used, say, x and y, and I tried to do Pythagorean theorem? Yeah, I have two variables. Okay, so unless you're going to be able to set up a system, which is two equations and two variables, you can't solve something with two variables in one equation. So we got to do something different.
Wait, isn't it like a special right triangle?
These are special right triangles.
Can't you just use that if you already have one in the numbers?
If you know the relationship of the sides here, then yes.
All right.
Does everybody remember the relationships for the 30, 60, 90? Nope, you're on the right track. That's, yeah. But does everyone remember it exactly? Probably not. So if you did, you could use that. But if not, then I'll show you how you figure it out. And then once you figure it out once, you don't ever have to do it again. Does anyone have a thought of how I can figure out one of these sides? By being clever. Okay, I have to make a copy of this triangle and do something with it. Okay, so I'll make a copy of it. But does anybody have a suggestion? If we knew right triangle trig, you could. But I'm going to pretend I haven't taught you that yet because I haven't. But you might know it from geometry. But we don't even need anything that complicated. We can do this just with basically geometry and being a little bit clever. So I'm going to make a copy of that triangle. Any suggestions on what I can do? I want to create a new shape using that triangle. Well, I could create a quadrilateral, and it would be a rectangle in this case. But that won't quite help me. What other shape could I create? Okay, another triangle. And how could I do that?
Like you can just double it.
If you look at the side between 30 and 90, and the other 30 and 90.
So you want me to put another triangle below it, or
Next to it.
Or
So
next
it's
to
a
it.
bigger triangle.
you want me to put it next to it? How about we put it below it?
Yeah.
So what I'm going to do is I'm just going to make a copy of it, and I'm going to put it below it. Okay. Now what do I have? Look a little closer. I have an equilateral triangle, right? 60, 60, 60. What does that mean? If you have an equilateral triangle, that means what? All sides are the same. So all these sides are 1, especially this side.
So those two equal.
Right, and these two sides are congruent, and they have to add to 1. So they each have to be a half. Okay, I don't need the bottom triangle anymore. I can get rid of it and now focus on the top triangle because I know the top side is a half. Right, so that's just kind of a clever way if you didn't know how to figure out that side, that you could figure it out, and it's 1/2. Now I can call the bottom side x and do the Pythagorean theorem, and then I'll be done. Okay, so how would I set up the Pythagorean theorem for this triangle? Yeah?
Is it x squared plus half squared equals 1 squared?
Yep, x squared plus half squared equals 1 squared. And then x squared plus a quarter equals 1. So x squared will equal 3/4. And my last step to get x by itself.
Square root.
And take the square root of the top and square root of the bottom. 2. Okay, so now I know the length of this bottom side is square root 3/2. So let's go back and look at our circle. you start at the origin, how far do you have to go to the right?
Square root of 3 over 2.
The length of the bottom side is root 3 over 2. And how far up do you go? 1/2. There's your coordinate for 30. Now, I want to take a look at 60. What's the difference between the triangle I have kind of laying on its side and the triangle I have standing up? What's the difference, yeah?
The one standing up, it goes over 1/2 and then up.
Yeah, so that means that the two triangles here are what? They're congruent. They're the same triangle. Okay? All that you've done is you've kind of taken this one and you've, let's see, if I, well, that would be in quadrant 2, but then I need to flip it the other way. So let's see if I can flip it. Okay, I guess that worked. So you've taken your 30, 60, 90, and now you just have it standing up. So the 30 is at the top, and the 60 is at the bottom. So since the two angles switch, that just causes the x and the y to switch. So what's the coordinate for 60 degrees? Square root 3 over 2. Okay, so with the 30, 60, 90 triangle, you do have to make sure you get the 1/2 and the root 3 over 2 in the right spot. Okay, so the way I remember it is if you draw your triangle somewhat to scale, okay, 30 is a smaller angle than 60. 1/2 is a smaller number than root 3 over 2. Okay, if you wrote these as decimals, root 3 over 2 is about 0.86 or 0.87. 1/2 is 0.5. So always make the short side 1/2. Always make the long side root 3 over 2. Okay? And if you remember that, you'll always get the 1/2 and root 3 over 2 in the right spot. Okay, so any questions on your coordinates for 45, 30, or 60? Okay, and just like I did with 45, I could take and do 150, which is a multiple of 30, just by reflecting the triangle from quadrant 1 into quadrant 2. Okay, and then you have to take into account negatives. All right, so let's see if we can find the 6 trig functions of 45, and then we'll do one of the 30 and 60s, and then we'll try some angles in other quadrants. For the first couple, I'll do all 6, but then eventually I'm just going to start doing the first 3. Okay? So if you want the trig functions of 45 degrees, what's the first thing you need to know? Meg? Yeah, you're going to have the coordinate. So the best thing to do is just memorize that coordinate. Okay, what's the coordinate for 45 degrees? Yeah, Kyle?
Square root of 2 over 2, common square root of 2.
Good. Okay. Now, what is my sine? And try to be specific so I know which one you're talking about. What's the sine here? It's the y, okay, which is root 2 over 2. How about the cosine? It's the x, which is also root 2 over 2. And the tangent, what's the formula for that? Y over x. So it's basically like you're just taking and putting a division line in right there and dividing. Yeah, you're dividing two things that are the same. Okay, so you get 1. Let's do the cotangent because that one's quick. To find the cotangent, what do you do to the tangent? Flip it, okay? It's the same thing. All right. What about cosecant? What would be your first step? And what do you do? And how did you get that? And to get cosecant, which one did you flip? Did you flip the cosine or the sine? The sine. Yeah, so we're going to take the sine value and flip it. That's how you get cosecant. In fact, that's also how you have to type it in on a calculator, because you don't have a cosecant button. Okay? And we'll talk about that too. Okay, so you get 2 over the square root of 2. Okay, but as Sophie did, you need to fix it. And there's even one more step we have to go from what she said. What would be your final answer? Just square root of 2. Because you'd get 2 root 2 over 2, and the 2's would cancel. So if that's your cosecant, what's, Cade, what would my secant be?
Let's see. 1 over square root of 2 over 2.
Yep, it is 1 over square root 2 over 2, which means to flip square root 2 over 2. And what do you get if you flip square root 2 over 2? And if you fix 2 over square root of 2, what would you get?
1 over square root of 2. I have no idea.
You're on the right track up till 2 over the square root of 2. But you're thinking about this one too much, because what I'm asking you, we've already done. Compare the sine and the cosine values. How do they compare to each other? They're the same.
So it would be square root of 2.
So the cosecant and the secant will also be the same. Because you said this, which is what we already did. So if your sine and cosine are the same, once you get the cosecant, just copy it for the secant. Okay. Questions on that one? All right. Let's try 6 trig functions of 30. So what's a little trickier about the 30 is you got to get the 1/2 and the root 3 over 2 in the right spot. So what I do is if I forget the coordinate, 30. All right, so draw your 30-degree angle. Try to make it to scale a little bit. So don't put it closer to 0. Draw your triangle. Okay. Now this is my short side. How long is the short side? It's always 1/2. This is the long side. Can somebody else tell me the length of the long side? Dave?
3 square root 2. Square root of 3 divided by 2.
Square root of 3 over 2. And now we're in quadrant 1, so both of these values should be positive. So my x is root 3 over 2. My y is 1/2. Okay, now we just go through and do the same thing we just did. Okay, so Kevin, what would be the sine of 30?
1/2.
Yep, would be 1/2. Okay, Bree, how about the cosine of 30?
Square root of 3 over 2.
Yeah, just square root of 3 over 2. And the tangent is what you get when you divide these. So just imagine dividing the sine by the cosine. If I do that, what would cancel? The 2's. You can either flip and multiply by the reciprocal, or whenever you divide fractions with the same denominator, it just cancels. So what does that leave me with? Yeah? Well, what's in the top? 1 over the square root of 3. Okay, so the 1 is in the top, square root of 3 is in the bottom. But we need to fix that because we're not going to leave the root in the bottom. So Allison, what would that fix if we rationalize it? Not quite. There will be a square root of 3 in it, but there's something else. Because if you multiply the top by square root of 3, you get square root of 3. But what if you multiply the bottom by square root of 3? Which is 3. So this is square root of 3 over 3. Okay, so good. Now leave the other part here because we're going to come back to that. when we do cotangent, okay? And we'll see, maybe we can use a shortcut. How about my cosecant? That's going to be 2. How about my final answer for secant? Yes, 2 square roots of 3 over 3. So you have to flip it, the root goes to the bottom, and then you'd have to fix it. Now for cotangent, you've got a choice here. You could flip this, or you could flip that. Which one is going to be faster? Yeah, the 1 over square root of 3, the first one. Because when I flip it, what do I get? Just square root of 3. If you flip the second one, that's fine, it'll work, but then you're going to put the square root back in the bottom, you're going to have to fix the whole thing again, and you're going to end up with the same thing. Okay, so those are your 6 trig functions for 30. Questions on that? All right, so now we're going to start skipping around to, well actually we'll do one more and then we're going to try going to different quadrants. This is asking me for the 6 trig functions of what?
60.
Yeah, that's 60. So what's your coordinate for 60?
Square root of 3 over 2.
Yeah, it's 1/2 square root of 3 over 2. Okay, so the sine would be cosine? Tangent? Yep, square root of 3. How about my cosecant? Secant? And cotangent? Square root of 3 over 3. Now, how do all those answers compare to the problem before?
They're the opposite.
Like the negatives?
No, they're like all the sine, cosine, and tangent are the secant, cosecant, and cotangent of 30.
All right, so the,
No,
not quite.
I screwed that up. I don't know.
So what happened, we do have the same answers, but can anyone be more specific about where the answers are? It's a little tricky, and there's a word for it, which I haven't taught you, which I will in a second. Oh, you don't have to tell me the specific word. Can you just describe what's happening?
Well, it's just like because the x and y are opposites, the sine and the cosecant of the first one is, or the cosine and the secant of the second one is. But they're just those two are split, and then the last one are 2.
So can you tell me again, what are the first two that flipped?
The sine and like the cosine and
Yep, the sine and the cosine switch places.
the cosecant and secant.
The secant and the cosecant.
And then the tangent and the cosine.
And the tangent and the cotangent. So does anybody see the pattern there? What's the pattern for the flipping? Yeah? Right, so the x's and the y's are all changing places, but in terms of the name of the trig function, does anyone see like how you can figure out what tangent goes with, or what secant goes with, or what sine goes with? There's a pattern in the name of the function. Yeah?
They all go with the code of.
Yes, they all switch with what's called the co-function. So sine switches with cosine, secant switches with cosecant, and tangent switches with cotangent. So those pairings are called cofunctions. Okay? All the cofunctions switch places. And in fact, that pattern always happens. Well, it does happen at other times too. So I'm not going to get into when else it happens, but it happens here. Okay? So those are called cofunctions. All right, so now let's try some stuff in other quadrants, and I'm just going to do sine, cosine, tangent. You would find the other ones just the same as we're doing, but we'll skip those. All right, so first thing you got to figure out is generally, is this angle a multiple of 30 or 45. Okay? That'll tell you whether or not you're going to be using your root 2 over 2s or your root 3 over 2s and 1/2. Okay, so what is 135? Yeah, it's a multiple of 45. So if you sketch it, it's 135. That would be 180 and 90. Now, how many degrees past 90 is 135? Right, so this section is 45, and this whole section is a 90. So that means this section would have to be 45. And that's why you have a 45, 45, 90. What is the length of each side in that triangle? Yep.
Square root of 2 over 2.
They're both square root of 2 over 2. But we're in the second quadrant. So just be careful when you write the coordinate. The bottom is negative. So can you tell me the whole coordinate, Maggie?
So it's negative square root of 2 over 2, square root of 2.
And square root 2 over 2. Okay, so there's your coordinate. And now we do the same thing. If you switch the x and the y value, this time you would get the sine and cosine wrong. You'd still get the tangent right. Yeah, but you'd get the sine and cosine wrong. So what's the sine here? Yep, square root 2 over 2. Cosine? And my tangent, negative 1. Any questions on those trig functions for 135? All right, let's try 7 pi over 6. Now, you can convert this to degrees like I've shown you before. You multiply by 180 and divide by pi. Or the way I do it in my head is I kind of use a shortcut. What's pi over 6? How many degrees? 30 times 7. 210. Okay? Any question on that? So that's a quick way, because if I know pi over 6, and it's just times 7. Okay? So 210. Is that a multiple of 30 or 45? It's a multiple of 30. So this is going to involve what two numbers in the coordinate? Yep. We just got to get them in the right order, and we have to figure out positives and negatives. Where is 210? Third quadrant, closer to 180, closer to 270, right in the middle. Yeah, it's closer to 180. So there's my triangle. What's the length of the long side? And the short side? 1/2. And they're both negative because we're in quadrant 3. Okay, so negative root 3 over 2. Negative 1/2. Okay, what's my sine? Yep, negative 1/2. Cosine?
Square root of
And my tangent. What did you say? The square root of 3 over 3, yes. Because when you divide it, the negatives cancel, the 2's cancel, and you're left with a square root in the bottom that you need to fix. Okay, any questions on that one? All right, so there's basically 16 different angles you can do. Okay, you can do the 4 that we studied yesterday. There's 0, 90, 180, and 270. And then you can do a 30, a 45, and a 60 in each quadrant. Okay? So there's all your angles. Now, are those all equally spaced? Well, what's the difference between 30 and 45? And between 45 and 60? How about between 0 and 30?
30.
And then between 60 and 90? So they're not all equally spaced. There's these big gaps that are to the left and the right of each quadrantal angle. And those would be the 15s, like 15, 75. There is a way to do the 15 and 75. It's very easy, but you need to know this first. Okay? And we are going to do the 15 and 75, just not today.
You're just gonna really have to.
I'll show you. There's a formula. You have to do this first and then plug in your answer to the formula, and it'll give you the 15s and 75s. Okay? But for now, this is what you need to know for the test. All 16 of these points, and I can ask you 6 questions about any one of them. I think there's only 3 or 4 of these on the test. Okay, so there's not a lot of it, but still you need to know it.
Yeah, so you're saying like 4 of those times 6 questions?
Well, 1 trig function per question.
Oh.
So this would be 3 questions on the test. So I think there's either 3 or 4 questions.
So that's 3 wrong answers.
Well, come see me, we can go over it. You missed part of it. All right, if you have an angle that's not a multiple of 40, 45 or 30, we're going to use the calculator. Well, if you're a multiple of 30, you're automatically a multiple of 60. I'm sorry, the other way around. If you're a multiple of 60, you're automatically a multiple of 30. So if you can't do something on the unit circle, then we just use the calculator. Okay? So I'm going to show you how to find the 6 trig functions of 42 degrees. Now, the first thing you have to do is, because there's 2 different ways you can measure angles, radians and degrees, you have to make sure your calculator is in the right mode. This problem is in degrees. Okay? So to change the mode, just press mode and go to degree. Okay, that's the only thing on the calculator today that's really new. Okay, does anyone feel they need to practice that? You press mode and then just change it to degree. That's it.
And then when you hit clear, does it automatically save?
Yeah, if you exit out, it'll always say at the top the mode you're in.
How do you even get to mode?
You press the button that says mode.
It's right next to second, right at the top, very top row. Okay, so put it on degrees. Always check your screen before you start typing stuff in. And then just press sine, 42, and that's it. Okay, if you want the cosine, just press cosine, 42, and that's it. And then the tangent, 42, press enter. Now, the directions did say to round all these off to 2 decimal places. So what would the first one be rounded off? 0.74. Okay. Now the other 3 you don't have buttons for. So how could I find the cosecant of 42? Yeah. Don't use the rounded off answer, okay, because it's not as accurate. If you want the cosecant, type it in like this. 1 divided by sine 42. Okay, so that's your cosecant. Does anybody have 1 divided by cosine 42, what the secant would be? Cody? 1.35. Okay, and how about the cotangent of 42? What'd you get, Dave?
1.11.
1.11? Other people get those answers? Okay. So that's one way they could ask you to do it. Or they could give you a problem.
What is the units on that?
The unit, there is no unit. That's a number.
Oh.
This number, when we get into right triangles, it's a ratio of 2 side lengths. So if it was inches divided by inches, the inches would cancel. It's just a pure number. There's no unit on it. All right. How about 6b? What's the difference there?
Wait,
If you just start typing stuff into your calculator right now, you will get it wrong
That's in radians.
because it's not in it's in radians. All right. So first thing you got to do is switch to radians, and now you can type it in. There's your sine of 10. Something like this.
Can you do this for 45 too?
It would give you decimals. It won't give you root 2's over 2's.
But then can't you do fraction of a decimal?
You can try, but it won't work. So there's your sine and your cosine. What would the sine be? Yep, negative 0.54, and the cosine would be 0.41. Okay, so that's how you can do it if it's not on the unit circle. Okay, any questions?
Why did you put cosine 20?
Oh. Negative 0.84. Thank you, I didn't mean to put 20. But if you wanted to know the cosine of 20, you got an extra answer right there for you.
I definitely needed that.
Yeah, you might need it, you never know. Somebody might ask you walking out of the room today.
Circle, I need to cosine.
All right, so in example 6, okay, the way we had to type in cosecant, secant, and cotangent, we had to basically flip something. Okay, and that idea is called a reciprocal. So I'm going to come back to that, and I'm going to write that down formally as what's called reciprocal identities. Okay, so I'm going to write that down in a second, but for now, I just want you to realize to get the secant, the cosecant, or the cotangent, there is a connection, and they are 1 over. Okay, they are reciprocals. Okay, but I will come back to that in a second. One thing you might have noticed is that when I ask you to find sine or cosine, you can find sine or cosine of any angle you want. Okay, there's no restriction on the domain. Okay, but watch what happens in the range. Okay, I want you to see what kind of answers I get. Let's take the sine of 10 degrees. Okay, sine of 59. Okay, sine of 87. Sine of 89. Sine of 90. Okay, sine of 95. It never is going to go above 1. Okay, sine of 120. Let's go sine of 190. I'm in degrees. How about sine 225? Sine 256.
Oh, it's gonna, the graph is gonna be like a wavelength look like, right? Is it just gonna keep going down from -1 to -1?
Yeah, it's going to stop at -1, and then it's going to start to go back up after that. So what I want you to realize here is the range never goes above 1, and it never goes below -1. Okay, any questions on that? That's true for sine and cosine. Okay, next pattern I want to take a look at is, let's look at the sine of 10. Okay. How would I get an angle that's coterminal with 10? Add or subtract 360. Okay. So do either one that you want and tell me what the answer would be. 370. 370. Okay. You get the same thing. How about if you had subtracted 360? -350. Same thing. So what do you think that suggests?
That they're all equal.
What's equal?
Coterminals.
Say it again?
Coterminals.
Yeah, coterminal angles have the same sine, and you could do it with cosine. Okay? So written as an equation in radians, you could write it like this. You can take any angle that you want, and you could add or subtract multiples of 2 pi. That's what 2 pi n means. You could add 2 pi, 4 pi, 6 pi, any multiple of 2 pi. I did it with you guys in degrees. So you could add or subtract 360. Okay, so if you want to say this idea in words, coterminal angles have the same sine and cosine values. And as an equation, that's how you can write it. And that's called the periodic property for sine and cosine.
What's n?
N is any integer.
Oh, all right.
So you can add like 2 pi times 1, 2 pi times 2, 2 pi times 3, any multiple of 2 pi, integer multiple. Okay, so where that might come in handy is if they gave you a problem and said, they want you to find the sine of 1,845 degrees, but write it as a simpler angle. Well, as long as you find angles that are coterminal, it'll have the same sign. So it's the same as that, or that. So it's really just like working with a 45-degree angle. Okay. Questions on that property?
So if I put in sine 45 degrees,
And sine of any of the other ones I had on the screen, they'd come out the same. Now, the last thing we're going to look at, and we're not going to spend a lot of time, we're going to spend probably 2 or 3 days on it at a later point, but not today, we're only going to spend about 10 minutes, is identities. What's an identity?
It's equal to itself.
An identity? Okay, so if you think of like the identity property for multiplication, it's like x times 1 equals x. That is the identity property. How about an identity as an equation? What does that mean if you're trying to solve an equation and it's an identity? Yeah, both sides are equal. So if I gave something like this, say like in Algebra 1, I put that on the left, and I put, let's say, 3x plus 2 minus x on the right. If I try to solve that, I'm going to get, let me change that a little bit. Now if I try to solve that, I'm going to get 4x plus 2 on the left, and I'm going to get 4x plus 2 on the right. So what values of x work in this equation? Any value. Okay? So an identity is an equation that is always true. It's always true. Okay, and we're going to look at equations that are always true that have trig functions in them. Okay, some of them you already know. Okay, it's basically the ones that you use to plug in secant, cosecant, and cotangent into the calculator. Okay, and those are called reciprocal identities. Let me make it bigger. So, reciprocal identities basically are when you flip a trig function to get a different one. So if you flip sine, you get cosecant. If you flip cosine, you get secant. If you flip tangent, you get cotangent. Yeah.
Can you like flip that back to the other one instead of missing?
Yeah, for an identity, you could just write an identity is an equation that is always true. And by appropriate or permissible values, I mean a value that wouldn't cause an error. Like if you had an identity that had a square root in it, you couldn't use a negative in that identity, because that would be imaginary. Okay, so appropriate values for your function. Now, if you flip the sine, you get the cosecant. What do you think would happen if you flipped the cosecant? you would get the sine. Okay? If you flip cosine, you get secant. What if you flip secant? You get cosine. And if you flip cotangent, you get tangent. Really, there's only 3 reciprocal identities on the board here. This one, and this one. If you're considering those other 3 as different than the first 3, that would be like if I gave you this, and you said that this is different than this. They're just rearranged. They're the same basic formula. Okay? You can always switch the denominator and what's on the other side and get a different version. Okay? Right? So these are really 3 reciprocal identities. The other ones are the same equation, just you've changed it a little bit. Okay? I could also write this. Cotangent times tangent equals 1. Okay? Why is that true? What did I do to get this one? Yeah, I just took this bottom one and I multiplied both sides by tangent. But, so algebraically we can see how I move tangent to the other side. But just logically, why is cotangent times tangent equal to 1? They're reciprocals. Anytime you multiply things that are reciprocals, you always get 1. Think of like 2/3 times 3/2. Everything cancels and you get 1. I'm not going to rewrite all 6 identities this way, okay, but you could. Okay, there's lots of different ways you can arrange them. All right, so again, those are the 3 important ones you want to know. The next 2 identities, I think we should already be able to reason them out based on what we've done. They're called the tangent and cotangent identities. And for the tangent and cotangent identities, let's go like this. What letter is sine equal to when we do unit circle? It's the y. What about cosine? And what about tangent? And remind me again, what's y equal to? Sine. And over cosine. So what does this 3rd row mean? Based on what I wrote there, you can say something else. Yes, tangent is the same as sine over cosine. So if you didn't have a tangent button, you don't need it, you could take the sine and then take that answer and divide by the cosine. And since tangent and cotangent are reciprocals, if you flip sine over cosine, that gives you the cotangent. Okay, so that's the second group of the fundamental identities. We have the reciprocal, the tangent and cotangent, and the last group is the Pythagorean. We are not using the Pythagorean at all today. The only reason I'm giving you them is so you have all the fundamental identities in the same spot in your notes. Okay, but for today, I'm not going to explain them. You don't have to worry about them. Okay, the first one is sine squared plus cosine squared theta equals 1. And if you're like, well, what does it mean if you put the 2 like that? It means what's on the right. Sine squared theta means to take sine of theta, get the answer, and then square that value. Okay, but that's how they usually write it on paper. That's how I have to type it in on a calculator. The next one is 1 plus tangent squared theta equals secant squared theta. And the last one is 1 plus cotangent squared theta equals cosecant squared theta. I usually just remember the first one because these other 2 are really just the first one. There's a way you can get the last 2 if you only know the first one. A 1?
plus.
1 plus?
I don't know why. It looks like-
Okay, so again, you don't need to know these for the test tomorrow. I just want you to have all the fundamental identities in the same spot. Right, now, these identities, we're not going to write them every single possible way you can, but you can rearrange them. So for example, if you took this first one, sine squared plus cosine squared equals 1, you can take sine squared and put it on the other side by subtracting it. This is not a different identity than what's above it. It's the same thing. Any questions on how I put sine squared on the other side? It's the same idea. Also, the reciprocal tangent and cotangent identities work for higher powers. So if you have 1 over sine to the first, that's cosecant just to the first. If you had 1 over sine squared, that's cosecant squared. 1 over sine cubed, cosecant cubed. Okay, you can use them with as high of a power as you want. We generally don't go above 2. Okay, same thing with tangent and cotangent. I could say tangent squared is sine squared over cosine squared. All right. So this is the kind of problem that's going to be similar to what's on the test. The goal here is to take something that they give you, and we're going to rewrite it simplified. Okay? So what you try to do, does everybody have what's on the left? Okay? You look at what they give you and try to rewrite it with just sines and cosines. And hopefully if you do that, something will cancel out. So looking back at the identities on the other page, how can you rewrite cosecant? 1 over sine times, and you can rewrite tangent 2 ways, but I like the way that Noel just said, sine over cosine. Now if you multiply those together, what happens? The sine cancels, and you're left with 1 over cosine, which is secant. So by changing everything to sines and cosines, something canceled out, and we were left with something simpler than what we started with. Okay, so the one on the test is either going to be something like that, or, well, example 8 is the same thing, something like that. Okay, you would do exactly the same thing. I'm going to have you try example 9 for homework. Okay, and we'll go over that before the test. Okay, so homework it's on 335, and I don't want you to simplify that. Just simplify example 9.
Did the other class have a different one?
Yes, but that's fine. You can do that one. The other class I did example 9 in class.
Yeah, I know, but then I won't know the answer to the one that they have to do. I would never find out the answer to that one anyway.
We can do example 8 in class too, so then you'll have both. Okay, we'll do example 8 before the test tomorrow.
That will matter, because I won't be here theirs.
I'll do it after school for you today. Okay, so try those problems on 335 and also example 9. Okay, and I will be after school today because our test will be